Hello and welcome to Bay College's Intermediate Online Lecture Series. This is section 6.3, part 2. Here we're going to look at rationalizing denominators. There are four things that we always have to keep in mind when we're dealing with radicals. And the first one is the radical should contain no negative or zero exponents. So if we have a negative exponent, we have to basically take its reciprocal. Now this would need some more work done to it, but this is just the example so that we recall that rule of exponents. Here, no zero exponents. Well, if we have anything to the zero power, we know that's 1, and if it's a factor, 1 times anything is that number. The second thing we have to consider is the radical can contain no factors with powers greater than the index. If we look at this example here, 4 is greater than 3, so we can simplify this radical and pull out one of the x. 3 goes into 4 once with a remainder of 1. 1x comes out, 1 remains. So we have x cubed rid of x. The next one is the index is as small as possible. If you recall in the previous section, I believe it was 6.1, we dealt with simplifying these radicals. Well, we have the 6th root of x cubed. Well, if we think 3 over 6 reduces to, I made a little error there, to 1 over 2. It's 1/2, right? 3 over 6 would be 1/2, so 1 and 2 as our power and index respectively. The next one is, and this is the one we're going to cover in this section, is a radical can contain no fractions under the radical. Then we can use the quotient rule, if you remember that. We could use the quotient rule here. And secondly, as part 4, the radical can also not be in the denominator. So we'd have to rationalize it, and that's the whole point of this section is rationalizing denominators. So I don't have an example for you because we're about to see several examples. Now if we go over here, we have the square root of 4/5. We notice there's a fraction under this radical. So we can use our quotient rule of radicals and rewrite it as the square root of 4 over the square root of 5. Now this is where we're going to learn how to rationalize the denominator. Essentially when we look at this, we say, if this was a perfect square, we wouldn't have any problems. We could just say, okay, well, if the index is 2, if it's a perfect square, I can deal with it. But this number here, 5, is not a perfect square. So what would I have to do to make 5 a perfect square? I'd have to multiply it by itself. So that's what we need to do. We say, what is the perfect power number of the index? So our index is 2. Essentially, I need 2 factors of that 5. I have to square it because my index is 2. But if we recall, we don't want to change the value of this expression. So what we do to the bottom, we have to do to the top. Now, if I multiply this out, the square root of 5 times the square root of 5, we could rewrite it as the square root of 25. But hopefully at this point in our math careers, we realize that the square root of 25 is 5. And then here we can use what we had talked about in previous sections. The square root of 4 times the square root of 5 is the square root of 20. We can multiply them because they have the same index. Now we have to simplify. While the square root of 20 was the factors 4 and 5, well, since this is 4 and 5, I can say, hey, 4 is a perfect square, so I can take the square root of 4, which is 2, square root of 5. Well, that's a little messy there. We'll clean that up. And we notice after these steps here, and sometimes it's long and drawn out, but we can see there's no radical in the denominator like there was here when we use our quotient rule. And there's no fractions that remain under any radicals. The only thing under the radical is part of the numerator. So let's look at this example here. We have the square root of 2x divided by 5y. We can use our quotient rule, the square root of 2x over the square root of 5y. Now, again, we just identify, well, the index is 2, so I need perfect square power numbers. Well, I need another factor of 5 and another factor of y under that square root. So I'm going to multiply it by the square root of 5y. Now I have 2 factors of 5 and 2 factors of y, so it is a perfect square. But what I do to the bottom of any fraction, I have to do to the top. I'm essentially only multiplying by 1, which doesn't change the value. Now if we do this multiplication, we get the square root of 25y squared. A perfect square, that's our goal. And we can just take the square root, so I'm going to kind of skip that step. I'm not going to write the square root of 25y squared. If I square a square root, I get what's under the radicand. And here, we can just multiply that. The square root of 2 times 5 is 10, and x times y is xy. Now here, there's really nothing I can simplify because there were no repeated factors. So we get square root of 10xy over 5y. Again, our goal was to rationalize the denominator, so there's no radical in our denominator, and the only, we still have a fraction, but the only radical is in the numerator. All right, let's look at this next example here. Well, we're not dealing with square roots anymore, we're dealing with cube roots. So we have to identify this and say, how many more factors of 2 do I need in order for it to be 3 factors, to have a perfect cube? Well, if I look at this, this one is not as intuitive as the last one. We're just rewrite the factor because we need 3 factors of 2. Well, I'm going to rewrite this as 3, or the cube root of 2 squared. Essentially, we want 3 factors of 2. Well, I have 1 here, and now I have 2 here, for a total of 3. If I multiply these together, I'm going to have 2 cubed. The cube root of 2 cubed is just 2. But what we do to the bottom, we must do to the top. And now if we multiply these, the cube root of 2 times the cube root of 2 squared. Now notice, these are the same, so it's only multiplying by 1. Oh, they weren't the same, were they? A little error there, but we got her now. They're the same, and we're multiplying by 1. So this becomes the cube root of 2 cubed, which is just 2. And here we have 3 times the cube root of 2 squared. Well, that's just 3 times the cube root of 2 squared, which is 4. We don't want to leave that power of just a number. We can actually do that math. And that's it. That's what we have to do. So we have to identify how many of these factors do we need. Well, I would need 2 more to have 3 of them to match the index. Now this one's a little bit different because we're going to undo our quotient rule of radicals. They have the same index. So let's rewrite this for a moment under the same index. 64a squared b to the 5th is divided by 9a to the 4th b squared. Hopefully we remember that rule of radicals, like we were able to split it up here. Well, we can also combine it here. And by doing that, I can simplify and decrease maybe some of these powers here by using my rules of exponents. Hopefully our rules of exponents are still fresh in our minds and strong from maybe a previous math class. At this point in math, we're supposed to know that. All right, so 64 divided by 9, they have no common factors. I really can't reduce that. But a squared over a to the 4th, well, we can use our quotient rule of radicals. 2 minus 4 would be negative 2. Well, negative exponent means that would be in the denominator. So I'm just going to take this over here and say the cube root of 64 over 9. 2 factors of a would remain in the denominator, right? 2 on top would cancel 2 on the bottom, so we'd have 2 left on the bottom. Well, here if we use the quotient rule, 5b to the 5th, 5 minus b to the 2nd, 2. 5 minus 2 is 3b cubed. Now, we really haven't done much other than simplified, some of the factors, so we only have to deal with b in one part of this fraction and a in one part of this fraction. But now I'm going to reuse that quotient rule. I know I worked it backwards here, and now I'm going to work it forward. That was just to simplify it. I'd rather just have this than all of these values. Now, if I take the cube root of 64b cubed over the cube root of 9a squared, now I can say, well, I could do some simplifying here, but my main goal is to rationalize this denominator. So I look at this and say, well, what is 9? 9 is 3 squared. It has factors of 3 twice. Well, I would need 1 more in order to have a perfect cube to match my index. So I'm going to multiply this by the cube root of 1 more factor of 3, because I already have 2. And I also have 2 factors of a here. I would need 1 more factor of a. So now I have 3 factors of 3 matches the index, 3 factors of a matches the index. When I do multiply this out, that radical is going to go away, but I always have to remember what I do to the bottom of any fraction I do to the top so I don't change its value. Now if we multiply this out, we're going to get the cubed root of 9a squared times the cubed root of 3a squared would be the cubed root of 27, a perfect cube, a cubed, a perfect cube. So let's just go ahead and simplify that. We're going to end up with, in our denominator, 3a. No more radical in the denominator. And when we multiply this out, we're going to get 3 times 64. Well, let's just leave that for a moment. The cubed root of 3 times 64, a, b cubed. Now we're ready to just simplify that radical. Well, what is 64? Well, we might recognize it as a perfect square. It's also a perfect cube. It is the perfect cube of 4. 4 cubed is 64. That's a perfect cube. So I can take it out. So when I simplify it, I'm going to get 4. And I can see that this b cubed is a perfect cube. b times itself 3 times. So what remains under that radical? Well, we have that factor of 3. And we have that factor of a. And that's it. Over our denominator of 3a. Now, lots of work here, lots of different steps, lots of rules of exponents to remember, and the quotient rule of radicals and things of that nature. It's a lot of work, and it's long and arduous, but with practice, we'll be able to skip some of these steps. We'll be able to see some of these, but it just takes practice. This is our final answer. Does it meet all of our requirements? Are there any more fractions under a radical? No. Is there any radical in the denominator? No. So we've met everything we need. And there it is. That's the answer. Lots of work, but we finally got there. All right, the next thing we're going to move on to is what if we don't just have factors in the denominator? Notice this is a different because it has some addition or subtraction to it. So what we have to do here is recall something we know from way back in the day is the difference of squares. If I multiply this out using FOIL, I get a squared minus ab plus ab minus b squared. And when I combine my terms, we can see, hey, guess what? I eliminated the middle term. Well, this is a powerful tool when it comes to rationalizing denominators that contain more than just one term, like we've seen in the previous examples. This has 2 terms, 2 and the square root of 3. We can use this to rationalize the denominator. Essentially, these are what are called conjugates. A minus b is the conjugate of a plus b. So when we look at this, the only difference between those two values is the conjugate is the change in sign. Because if we FOIL this out, the middle term, like here, had gone away. That's what we want to happen here. We want to have a perfect square and a perfect square, so we're eliminating the square root. But we also have to remember what we do to the bottom, we have to do to the top. So that we are essentially multiplying the top and bottom of this fraction by the conjugate of this term here, the one that contains the radical. So if we multiply that out, well, 1 times the top is 2 square root of plus square root of 3 over, if we FOIL this out, we know these middle terms are going to cancel because it is the difference of squares. So I get the first term squared minus the second term squared here. Well, the square root of 3 times the square root of 3 is the square root of 9. And the square root of 9 is just 3. And now we can say, hey, 4 minus 3, there's no more radical here. I can actually do this math. 2 plus square root of 3 over 1. Well, being over 1 isn't necessary, but sometimes that isn't going to be 1. But if we simplify it, it's just 2 plus square root of 3. Does this fit our criteria? Do we have a radical in the denominator? No. 2 plus square root of 3, so it did simplify. Now, if we look at this example, we want to rationalize the denominator. I see radicals in the denominator. Well, even though we have 2 of them, it still can be eliminated by using its conjugate. So what is the conjugate here? Let's identify the conjugate. Well, it's these 2 terms, but instead of subtraction, we're going to use addition. 2 square root of a plus square root of b. That is its conjugate. And what I do to the bottom, I do to the top, so I don't change its value. I'm still multiplying by 1. It's an ugly looking 1, but it's still 1. So when I multiply these out, on the bottom, I know it's the difference of squares, so the first term squared, 2 times 2 is 4, square root of a times square root of a is a, the square root of a squared, which is just a. So I get 4a. And the second term squared minus the square root of b squared is just b. So this is my denominator. So I'm going to write it over here. 4a minus b. No more radical in the denominator by multiplying by the conjugate. Now the top's a little bit different. It's good review from what we've seen in the previous video. We have to FOIL this out. So if we FOIL it, 2 square root of a times 2 square root of a is 4a. And then we have 2 square root of a times square root of b is 2 square root of ab. Same index, we can just combine them under the radical. Negative 3 square root of 2, oh, excuse me. Negative 3 times 2 square root of a is negative 6 square root of a. And negative 3 times square root of b is negative 3 square root of b. Just continue that over there. And we can see, do we have any like terms? Just like in the previous video, we have to make sure we can combine those. There are no like terms. That's essentially my answer. We have 4a plus 2 square root of ab minus 6 square root of a minus 3 square root of b all over 4a minus b. And there's nothing we can simplify, nothing we can factor out. It is what it is. Now it's not pretty, but there are no more radicals in the denominator, and that's essentially our goal there. All right, so let's talk about using these tools when we divide expressions that contain radicals. We have essentially these 4 steps when it comes to simplifying or dividing radicals. The first thing is to simplify. If we can simplify anything, it's going to make our math a little bit easier and not as tedious. When we're dividing, the key is to factor. All semester long, I'll say factor, factor, factor. When in doubt, factor it out. A little rhyme for you. Please, strengthen your factoring skills if necessary. And because we are dividing, we're going to be essentially dealing with fractions. So remember to always reduce. And then finally, if we've simplified and we factored and we reduced, we got to make sure that we meet the criterion that there are no radicals in the denominator. We need to rationalize the denominator and simplify further if necessary. So let's move over to an example here. Here we have 2 square root of 15 plus 5 square root of 8 is divided by 12. Is there some simplifying I can do? Well, I can say, well, the square root of 8, I know 8 is 2 cubed, so maybe I could pull out a factor of 2. Let's do that. 2 square root of 15, 15 is just 3 and 5, so no repeated factors. I can say, well, I can take out that 2 times 5, which is 10 square root of 2. Because 8 was 2 cubed, I can take 1 out with a remainder of 1, all over 12. So we did a little bit of simplifying. That was step 1 here, simplify. And now we can factor. What do these terms have in common? Well, they're both containing a factor of 2. It's 2 times this and 10 times that. 10 has a factor of 2. So let's just factor it here. 2 times the square root of 15 plus 5 square root of 2. So I just factored out a 2, and now we can actually reduce. 2 and 12 have a common factor, so I can reduce that. 2/12 would reduce to 1/6, so we just reduced it. Now, do we need to rationalize? No, there's no radical in the denominator in this case, so this is done. Now, I want to just make sure you don't do the cardinal sin of reducing here. If students cancel these right away, you're not going to have the same answer. That's illegal operation. You can't cancel from a term, only a factor. Okay? When you see addition or subtraction in there, factor before you try to do any reducing. So if we do factor, simplify, factor, and then reduce, we're where we need to be. All right, we have one more example, and I really, really like this example because it incorporates just about every concept that we've used so far in section 6.3. If we look at this, we see, oh, there's radicals everywhere, there's radicals in denominators, it's essentially one big ugly fraction. Well, the first thing we want to do is let's rationalize this denominator. So how do I rationalize this denominator? Well, it has two terms, so I'm thinking I'm going to use a conjugate. So I see subtraction, I know it's going to be addition of these terms. 4 square root of x plus, plus 2 square root of y. And what I do to the bottom of any fraction, I'm going to do to the top, so that I'm essentially multiplying by 1. And now we have to do lots of multiplication. Well, if I recognize the conjugate as just being the difference of squares, I'm going to square the first term. 4 squared is 16. The square root of x squared is just x. Minus the last term squared here. 4 square root of y squared is y, so we get 4y. This is my denominator. And now on the top, well, if we recall from the previous video, we have to use the distributive property because we have a single term times a binomial, right? So we're just going to distribute. 2 square root of a times 4 square root of x is 8 square root of ax, right? Same radical, we can combine those terms under the radical. And then this times the next term would be 4 square root of ay. Now, is there anything I can simplify here? Well, let's check. Let's see, does this actually combine every possible thing we've worked with in this section? Well, I see 8 and 4. I can factor out a factor of 4. And that's going to leave me with 2 square root of ax plus square root of ay. Different terms because what's under the radicand is different. Here, well, I can also factor out a 4 here. And that's going to leave me with 4x minus y. And now we can see, now we can actually reduce because we factored. And we can say, hey, we have this common factor of 4. 4 over 4 is 1. Or we can just say, let's cancel them, right? Common factor. And our final answer is 2 square root of ax plus square root of ay all over 4x minus y. This is our final answer. It was a lot of work to take this and rationalize that denominator so that we had no more radicals in the denominator. This has been part 2 of 6.3. Thank you for watching.